All right, and welcome back, everybody. So, last time we were talking about how diagonalization could be seen as figuring out what the geometric properties are about matrix multiplication, and we wound up with this nice little visual of what the decomposition Q times D times Q inverse, which was really Q transpose, looked like from a geometric point of view. But the real takeaway here is that symmetric matrices are always diagonalizable, and more to the point, that they're diagonalizable with eigenvectors that are orthonormal. Right, there is an orthonormal basis for Rn based on this matrix A. And when we have a complex symmetric matrix, well, in this case it wouldn't be symmetric, it would be Hermitian, so self-adjoint is another word, or it's equal to its conjugate transpose. All of those are equivalent, and we would still wind up with this sort of setup, but instead of Q being an orthogonal matrix, it's going to be what was called a normal matrix, where instead of Q times Q transpose gives you the identity, you get Q times Q star equals the identity matrix. But I digress. That's where we left off last time. What we want to be able to do is extend the success that we have for diagonal matrices, or for diagonalizable matrices, into the more general setting for matrices that either aren't diagonalizable but are still square, or that are actually diagonalizable in a more general sense, where they're actually rectangular matrices. And that turns out to be a bit of a problem for us because we only know how to come up with diagonalizations for matrices that are square. So let's see if we can't find a way to just kind of skirt around that and make up for that shortcoming. And a key observation we'll make is that A, even though it might not be square, both A transpose and A transpose A are. So more to the point, these guys are symmetric. So both of them are diagonalizable. But it's actually, you've seen in your homework that it's more natural to consider A transpose A in this case, because this guy is always positive semi-definite at the very least. So it is a positive matrix, A transpose A. So the matrix A times A transpose is going to be more of what we call a projector matrix. And you've seen this in your homework, that A times A transpose really corresponds to a sort of orthogonal projection. But we won't worry about it right here. We're going to take a look at the Gram matrix A transpose A, because this guy is symmetric and he's positive. The spectral theorem then guarantees a particular decomposition of this matrix. So it may not be a decomposition of A that we come up with in this case, but we can kind of force ourselves into a decomposition for a matrix related to A. And what we're going to do is factor out exactly A transpose A into its spectral decomposition, and this will be effectively the diagonalization that we know and love. So in this case, we're going to go a little bit further here. So what we would like to say is that, okay, we have the decomposition that we want for A kind of hidden in here in this Q times D times Q transpose matrix. And the idea would be to split this guy up into two very similar pieces. And in fact, these guys are transposes of one another. So really, we would like A to just be the right-hand portion of this decomposition. But it's still not quite right to say that, right? Because this is definitely not the case, right? A is not equal to this sigma times Q transpose. These guys may not even be the same dimension, right? So we need to find a way to solidify that idea, but make it a little more rigorous. Try to find the correct way of splitting up A transpose A into pieces that look like A and A transpose respectively. So we're going to go ahead and define the singular values of the matrix A. And A is just an arbitrary rectangular matrix. For right now, we're going to consider real matrices. There is an argument to extend this to complex numbers, but we're not going to worry about it for right now. So the singular values, sigma 1 through sigma r, so notice r may or may not actually be equal to the rank, or may not be equal to the minimum between m and n. But these singular values are the positive square roots of the non-zero eigenvalues of A transpose A. So the non-zero elements of this D matrix upstairs are going to be kind of our analog for eigenvalues for the matrix A, or at least their square roots will be the analogs of eigenvalues for A. The associated eigenvectors that we get here are called the singular vectors. Right, so again, these singular vectors are not they're not going to correspond to any null spaces. Right, we need to make sure that all these singular values are positive numbers. Therefore, none of these sigmas are going to correspond to the null space of A or A transpose A. So the convention here is to line these guys up, order the singular values from greatest to least. Right, so first of all, how do we know they're all positive? Well, again, it's because A transpose A is going to give us, there he is. Oh, shoot, did it again. A transpose A is a Gram matrix. So that means that its eigenvalues are always non-negative. So we can just compute square roots. So this A transpose A has non-negative eigenvalues. Therefore, I can go ahead and take the square root of each and every one of them without penalty and still come up with real numbers at the end of the day. So we're going to order these guys from greatest to least, and that'll be sigma 1 bigger than sigma 2, all the way down to sigma r. And all of these guys are going to be positive numbers by definition. Sigma 1 we're going to go ahead and call the dominant singular value. Right? This guy is going to be the largest contributor to something, some property of A, like the biggest part of A, the most impactful part of A, the most dominant part of A. So we just want to make sure in this convention that we don't count 0 to be a singular value. Matlab does this, kind of, and I'll show you in a moment when we talk about the example at the end of the section or at the end of the video. But we're going to make sure that the singular values are positive numbers. Now, if A happens to be symmetric, then sigma is going to be equal to some absolute value of the absolute value of some eigenvalue. Right, and you can, screw it. I'm going to go ahead and pull this up. No, wait, not that one. No, we're going to pull up Matlab, and Matlab's going to go on the left side of the screen. There we go. So let me go ahead and clear that and see if it wants me to wake anything back up. Yep, reconnect. Please pay no mind to the man behind the curtain here. I have an active session. Yes. Go ahead and start it. It's okay. La-di-da-da-da. I swear, every time I begin the videos, I have logged in and logged back into Matlab, but these, for some reason, log me out within like 5 minutes. It just kills me. But anyway, the example that we're going to have at the end of the section here is this matrix given by A. So feel free to follow along here. The command that you're going to need to know for Matlab is just as simple as it sounds. We're going to make SVD, because we're trying to create the singular value decomposition. So let me show you. It's going to spit out 3 matrices for you, and we'll see how they go back together momentarily. But SVD is effectively what's going to give you your eigenvalues for this rectangular matrix. And S is going to be the matrix that contains those guys. So notice, no zeros on the diagonals, right? Singular values are positive. However, this U matrix repeats the first and third column. So that's what I mean by kind of, they kind of do the right thing. We're just making sure that we zero out any superfluous vectors in this U matrix. We'll talk about that momentarily. Coming back to the point at hand, well, let me go ahead and create this matrix, -4 by 1 by 1 by -4. And this guy, I can go ahead and compute the eigenvalues for this. Sure, you can go ahead and compute them yourself. You know how to do this. But you can verify they're both negative. However, if I were to create little u, little s, little v as the SVD of this matrix C, notice what happens to the S matrix. The S is still comprised of positive numbers. This is because A transpose A, or C transpose C in this case, is a Gram matrix, and that is a positive, at least semi-definite matrix. So that means that we don't quite get a diagonalization as we did before. This singular value decomposition is going to give us something that orders the dominance of the eigenvalues. Right? So what we should think of here is, in the symmetric case, if A is equal to A transpose, then the singular values are the absolute values of the eigenvalues of A, and the singular vectors are the non-null vectors. So in other words, we need to make sure that all the eigenvalues we take here for our singular values are non-zero. So that means that we can't be using any vectors that belong to the kernel of A. Right? So we're just omitting all the non-null space vectors. So for any rectangular matrix with A transpose A equal to Q D Q transpose, we should think of Q as containing the eigenvectors of A. And effectively, the square root of this matrix D is going to be the diagonalized version of A. So we just need some smart way to break up Q D Q transpose into equal symmetric pieces, or at least transposed pieces, such that we can go ahead and make this connection upstairs that this matrix A is actually kind of linked up with this sigma times Q transpose. So let's see if there's a smart way to do this. I bet you, since I'm talking about it, that there probably is a slick way to do this. So let me show you. We have the following theorem that shows us how to break up these pieces, or tells us what these pieces look like. So this is our singular value decomposition theorem. So a non-zero rectangular matrix A with rank R can be factored into something that looks like P times sigma times Q transpose. So we're very close. A looks kind of like sigma times Q transpose, but there's this extra factor of P here. And P is an M by R matrix, and Q is an N by R matrix. These guys are composed of orthonormal columns, right? So these are not orthogonal matrices because they're not square. However, they do behave like orthonormal or like orthogonal matrices, at least in the P transpose P and Q transpose Q departments. So we also have a matrix sigma, which is effectively acting as the square root of the diagonal matrix, the diagonalization of A transpose times A. And this sigma is going to contain the non-zero singular values of A. So to give you an idea of why this might be the case, let's walk through an example. Right? And this was the A that I gave you just a moment ago in Matlab. We can go ahead and compute that A transpose A. You know what? I can go ahead and verify this. Let's go ahead and just keep this guy. Oh, there we go. Oh, come on. You knew it. Okay, let's go ahead and keep these examples on the page. So coming back here, let's clear the screen. A, just to remind you, yes, that is the correct thing that I have in Matlab. And we can compute A transpose A is indeed, ooh, I wrote it down wrong in the lecture notes. Shame on me. Yep, so let's go ahead and fix that. There we go. So it's 3 by minus 1 by minus 1 by 3. However, I can go ahead and create what Matlab calls the singular value decomposition, and it will be A transpose A. It'll be given by these matrices. Now you might see numbers that are very similar, that are like up to a negative sign, just to make sure that they are symmetric, because Matlab likes symmetric things just as well as it likes rectangular things or square things. But the point is that I can go ahead and break this guy up into the following decomposition. Right? So this is exactly the fact that A transpose A is diagonalizable. Okay, so I think the only place where we're different here is in the ordering of the vectors and up to a minus sign. Yep. But the point is, S here is composed of, well, it's supposed to be this square sigma matrix. So if I take the square root of this guy, I come up with sigma. And sigma is going to be 2 by root 2 down the diagonal of a 2 by 2 matrix. Okay, so notice this is a 2-dimensional or 2 by 2 matrix, but A itself is a 3 by 2 matrix. So that means that sigma is really going to be a square matrix that's given by, or whose dimension is given by the rank of A. And I can double check that. The rank of A is indeed 2. All right. So that's why we have a little index R standing for rank. So notice what happens here. If I do take A and multiply into it, so A star 1 over square root 2 by negative 1 over square root 2. Oh, come on. Oh, yeah, that means I just wrote it down wrong. Squirter? No, squirt. Oh, yeah, squirt, not squitter. Squatter. Squirt. There it is. Notice that we wind up with something that is a singular value times a unit vector. So this is square root of 2 times the vector 0 by 1 over square root. Oh, come on. 1 over square root of 2 by 1 over square root of 2. And sure enough, that's exactly this. It's going to be some matrix that I want to use here. It's going to be effectively one of my principal vectors. So this new vector here, 0 by 1 by 1, is acting like an eigenvector for A, since I can go ahead and factor out a singular value from this guy and get a unit vector in return. Notice that I get the same thing. By the way, I'm getting these guys from up here. Okay, so this guy goes down here, this guy goes down here. So these are, I'm not just pulling these out of thin air. I'm just making sure that when I multiply A into these vectors, that I wind up with something that makes sense, something that looks like an eigenvector. And sure enough, if I multiply A into 1 over root 2 by 1 over root 2, then I can go ahead and factor out another singular value here and come up with a unit vector 1, 0, 0 on the outside. So that means if I throw those two operations together into one matrix multiplication, I wind up with A times, this is effectively Q transpose, and then I wind up with, is it? No. This is the Q that I want, right? Because I want a Q transpose at the end of this. And this guy I'm going to go ahead and call a P. Right? This is going to be my principal vectors, P for principals. So notice what happens here. Because this matrix Q is composed of an orthonormal basis of columns, it's an orthogonal matrix, so that means that its transpose is equal to its inverse, so I can go ahead and flop the Q over to the other side at the cost of adding a transpose. And this is exactly the decomposition I was looking for. Okay, so there's the proof of concept. This does work. We can do this. Let me show you how to do it more generally to show you that it actually does still work in the general setting. So let's do it again, very slowly. Right, first step here is to go ahead and compute a diagonalization of A transpose A into orthonormal eigenvectors. So this will give me a full n by n decomposition, or set of n by n matrices, Q and D, along with Q transpose. So notice at the end here, there very well could be some eigenvalues that are equal to 0. It is okay. That's not bad just yet. Okay. So what we're going to do is observe that through orthogonality, this relationship here will allow me to rewrite these to rewrite D in the following way. I can go ahead and take the Q here, multiply on the left by a Q transpose, and then take this guy, multiply on the right by a Q, and I'll wind up with an expression for D. Right, we've seen this before. This was effectively our S inverse AS decomposition for a diagonalizable matrix. So no problem there. This is the same exact thing. Right? It's nothing new yet. And what we notice at this point is that I can go ahead and break this guy down, not into the associated the association that I have right now. I can reassociate these parentheses, and notice that AQ transpose shows up on the left and AQ shows up on the right. So awesome. That's looking more and more like something that we want. But then we take a look, right? We have a whole bunch of extra potential zero eigenvalues that we need to get rid of. So this sigma, I'm going to take to effectively be the square root of D, right? This is what we were doing before. So that D is actually equal to this guy. D equals sigma 0 squared, right? That's exactly what I want. 2, 3, 4, and get rid of that one as well. And from this sigma 0, we're going to remove all of the zero eigenvectors and eigenvalues. So from sigma 0, we're removing eigenvalues, and from boldface Q, we're removing the basis of null, the basis on the null space. So this subset, because it came from an orthonormal set, is still orthonormal. Therefore, Q transpose Q, this new Q, right? This guy where I took away all the zeros, like all the null vectors, take those guys, put them into one matrix, call it a regular Q instead of a boldface Q, and we're going to wind up with something that behaves like an orthogonal matrix, even though it's not a square matrix. So very similarly, we're going to remove the lambdas r plus 1 through Rn, or lambda r plus 1 to lambda n from sigma 0, because I know that there are that many, because R is the rank of this matrix, and anything beyond that is going to be contributing to the kernel. So that means I have an n minus r dimensional kernel. So I need to get rid of that many singular values, which means I need to remove those eigenvalues from sigma 0. And technically these would be square roots, is that right? Yeah, these are square roots. Let me go ahead and fix that. Square root. But technically, yeah, screw it. They're all 0 anyway. All those are 0 eigenvalues. So that sigma squared here, if I took away all the 0 eigenvalues, then I wind up with sigma squared is equal to A times Q transpose times A times Q. Right, notice this is actually smaller, right? There are fewer vectors in this Q matrix as opposed to the one that I had upstairs. Okay, I am less n minus r vectors from my null space. So because this sigma square is diagonal, the columns of A times Q have to be orthogonal, right? It's not orthonormal, but all the off-diagonal entries of sigma squared are telling me that the dot products, the Euclidean dot products between the columns of A times Q must be 0. So the only place where they're non-zero is on the diagonal. So this is an orthogonal set of vectors that make up the columns of A times Q. So once I'm here, I can go ahead and scale this guy down by effectively dividing a sigma on the left and on the right, so that I wind up with this fellow. And this is effectively what we're going to take to be P. Right? So P is actually something that we don't get from the diagonalization up front. It's something that we have to create from the diagonalization of A transpose A. So these vectors are actually fairly costly to produce, but there are nice algorithms to get them quickly. So we thereby create the matrix P, and that's A times Q times sigma inverse, right? Because the fact that bold Q was an orthogonal matrix, not only do we have that Q transpose Q and Q transpose are equal to the identity matrix, they share this property with Q transpose Q. So the regular type set Q as opposed to the boldface Q. Not only do I get the Gram matrix between an orthonormal set of vectors, but if I go ahead and reverse that, the projector matrix is actually a larger matrix, but it's the identity matrix. Right, this is the identity matrix, and I think it's actually up to a certain point. Like there would only be R non-zero entries in this guy. But Let me think about that. Is that right? No, it actually fills it up. It actually does give me the identity matrix. So at the end of the day, what we wind up with is the fact that P is defined thusly. I can go ahead and multiply the sigma on the right. I can multiply the Q on the right by a Q transpose. That way these guys go away into an identity matrix, and I wind up with what is known in the trade as the singular value decomposition of A. All right, so there is a way to break this guy up, even if it's not square, even if it's not diagonalizable, there is a way to break this guy up so that he looks diagonalizable. That we still wind up with the same sort of geometric properties that we did in the previous video. And more to the point here, if A happens to be diagonalizable, then yeah, we do wind up with something that looks like a diagonalization. But we made the comment earlier that the SVD is not the same thing as a diagonalization. We had that matrix C to show it to us. So if I checked the eigenvalues once more for C, they're negative. But if I wind up asking for the SVD of C, it's just going to give me the the singular values of this matrix C. And those are the absolute values of the eigenvalues of C. So it's not quite the same thing as a diagonalization. It's very close, very closely related, but again, it's giving us a way to assign dominance to the eigenvalues. Right, so let's go ahead and finish up this section. I know the video is running a bit long, but bear with me, we're almost out of the woods here. And I just wanted to double check that indeed, the thing that we computed before, you can go ahead and throw this into Matlab. By all means, check it out. This guy does diagonalize in the way that we saw before. We can go ahead and create sigma zero by just using the square root of d, right? There's no problem in this case because there are no zero eigenvalues, right? There are no zero eigenvalues for this guy. So P is just going to be whatever this matrix A is times Q times sigma inverse, and there's the P matrix from before. We do see exactly the same thing. Right, and the last thing to talk about before we stop that section, before we go into applications, some things to note. A and A transpose share the same singular values, but they don't necessarily share the same principal vectors. In fact, they're kind of opposed to each other. They are transposed versions, effectively. So the singular vectors I get in A are actually the columns of P, but the singular vectors that I get for A transpose are actually the orthogonal matrix Q, or are the columns of the orthogonal matrix Q, or the thing that looks like an orthogonal matrix. Both P and Q kind of look like orthogonal matrices, come to think of it. But the point is that these guys share the same singular values, not necessarily the same principal vectors or singular vectors, but the same singular values for sure. So, second corollary is that the columns of Q form a basis for the co-image of A, but the columns of P form a basis for the image of A. Kind of interesting that that holds up. So that means that Q is going to be really helpful for us in figuring out least squares problems, because I know that my minimum length solutions, or close solutions, my minimum length solutions to a system that has infinitely many solutions is going to be a unique vector that lives in the co-image of this matrix. So if I'm going to go ahead and kind of prove this to you, or at least give you a proof of concept, note that both P transpose P and Q transpose Q must be equal to the r-dimensional identity matrix. Sorry about that. Where R is the rank of A. Therefore, the columns of P and Q are not only orthogonal, but they are orthonormal. And because there aren't any zeros along those columns, there aren't any zero vectors in those columns, these columns are linearly independent. Right? There are R of them, so they must also span the co-image and the image of A, respectively. So instead of showing that they're linearly independent and span, I'm going to do something different and use the fundamental theorem of linear algebra to show that, sure, they're linearly independent and there's the right number of them. All right, they already automatically span the spaces that I'm looking for. All right, and that's where we're going to go ahead and kill this video. So yes, a singular value decomposition does exist. It doesn't have to be unique, but there is a way to diagonalize non-rectangular matrices. So in order to see what we do with them, let's go ahead and jump over to the next video, and I will